Thank you for the nice introduction. And in academia, we don't also think of like a boss and employer-employee relation. I think Eric would share what I'm gonna say is that as academic leaders, we think of ourselves is to serve the community by creating a stimulating and intellectual environment where we want to see the kind of intellectual creation, you being your brilliant self and then contribute to innovations that will benefit the society. So I'm very proud to be the boss of such a department, and then I'll be more than happy to tell any of you what was going on at Columbia, after the talk. So thanks for the invitation. I have learned a lot from all the meetings that I have had, and I look forward to have more meetings later today. And this is one of the most exciting university I have visited. Is so young and so different and so innovative, and I feel honored to be invited to be here. So today I'm going to talk about a little project of mine. So I'm a statistician. There is one famous saying in statistics is that the best thing about being a statistician is you get to play in everybody's backyard. What that means is that statistics is a methodology field where you can contribute to many scientific research, and then you don't have to commit yourself to one particular application domain. And then for me, I am very curious in many ways. So I feel very fortunate that my research has touched upon biology, social sciences, climate sciences, ecology, and I also find other opportunities to collaborate with humanities to have important discussion about things like data ethics, because I feel as a technical field, sometimes we don't need to or don't want to be the people defining things as fairness or privacy when that topic has been debated for thousands of years, right? So that's just a little bit background about myself. So today I'm going to talk about a talk called for community detection using large networks, where leveraged one of methodology that I developed for a social science study. So it's a collaborator with my former students and a colleague, John Paisley, who was, I think, David Bly's former postdoc, and then now currently a tenured professor in the electronical engineering department at Columbia. So networks is an interesting topic because computers are very good and statistics are very good at analyzing vectors of numbers, and then we realize the world is actually more interested and organized by relations. A lot of times it's interesting to look for patterns in vectors, but also it's interesting to look for patterns in interconnections of entities. So here, social network is the structure of relationship between nodes, individuals, actors, egos, depends on where you publish your papers. Here are the words that you call them. And then community detection is one of the possible ways or possible direction where we're interested in such data. And here I put a short informal definition of community detection is a search for groups of nodes, group of entities that are densely connected and exhibit similar connectivity patterns within and between groups. So here I highlight two words. One is densely, which means that you are expecting that people belong to the same community should be connected to each other more, which is not necessarily true in some cases. And then the second is similar, is that you're assuming that people belong to the same community will interact with other group of the bigger population in similar way. So these are actually statistical definition, right? Density means higher frequency, and similar means common patterns. So this is the kind of assumption we're using. So a bunch of tools are available. Spectral analysis is treating the network data as matrices, and then you apply linear algebra and using some mathematical tool to detect the dense connection and or similar connection using the single letter decomposition of the network matrices, and then which is exactly based on the assumption. And then there are another bunch of methods are called model-based clustering or model-based community detection, which we have the expert in the room that have written many papers on this topic. They start with a very simple model, piggyback on the definition I just said, density connection, similar patterns. So you imagine that the population can be partitioned into groups, and the groups form a simpler matrix, a lower dimensional matrix, and is higher value on the diagonal, a lower value on the off diagonal, and then have a similarity. So that led to the stochastic block models. So if you read this literature on theoretical properties of these algorithms, the stochastic block model have led to a lot of theoretical guarantees about the recovery of such groups, the oracle properties, so on and so forth. But the stochastic block model have the rigid assumption that everybody can belong to one group, and then one group only, which is not true for our real world assumptions. So for example, when I have social interactions with others in the network, I wear different hats. So sometimes I'm a data scientist, sometimes I'm a university professor, and sometimes I'm a parent at school. So we all have different roles we play in the society, and that different roles lead to different kind of interaction. So which led to a very influential paper by Eric in 2008 and his colleagues at Carnegie Mellon that called mixed membership stochastic block model, which make the following assumptions. We assume you have D communities, and then you have the what I call the global connectivity, the overall connectivities. You believe this world can be partitioned in D groups, and then between groups there are how it's organized, right? How a parent of a school age children interact with the university professor, for example. And then each node's membership in the D groups follows a probability vector. So say in my day-to-day life, I am a professor 50% of the time, and 30% of my social interaction is on the parent friend, and 20% is on being Asian or being a immigrant in a Western country, for example. So these are the how this model organized for each pair. So the network is all about relations. For each pair of nodes I and J, that we define membership indicator vectors as senders and receivers. So say when I have an opportunity for social interactions, I will assume a membership. So I will assume my university professors, and then another person in the network will assume being a parent, and then the probability of we forge a social tie will follow a Bernoulli, which is random flip a coin, according to a probability that defined by, let me check the, I think it's easier using cursor, even we have a Zoom audience. And then by assuming this product by the sender and receiver and B. So these are the notations. And then you have so we have Yij will be the edge or arc or link, or no matter how you call it, for network data that you observe in the real data. So it could be, it's a random outcome based on the probability defined by group membership and then driven by probability. And this model has been extended. Here I include a few more papers from Eric, and here is Lisan, and here that has been extended to study more complicated behaviors, such as you assume a state space for dynamics. So here is a screenshot of the model from this 2010 paper, which was one of the first machine learning paper published in the Annals of Applied Statistics. So the second, and it can also be further extended. And here, this diagram uses a slightly different notation. but you have the B matrix here being called beta, and then you have sender receivers throughout. And this network has been used to study multiple dynamic networks, such as a blogger space, or how senators in the U.S. Congress vote on different resolutions. So the mixed membership stochastic block model has very nice features, make them very useful in practice. One of them is that it uses the same Dirichlet prior distribution as topic modeling, so make it a very natural choice when you want to study connections that also have node information where you want to jointly model both of the latent structure, latent grouping structure, clustering. So it has, however, on the other hand, being powerful, it also have a large number of latent variables or hidden variables or parameters you need to estimate. It's set up as a Bayesian model. Computation can be rather expensive because study network, you need to deal with a node, a large number of nodes, but real world network is very sparse. The way to think about it is that here you have 1 million population or 7 million plus visitors, you have multiple million population, but on average, from day to day, your interaction with a couple dozen people, or collectively, you know, about a few hundred people. So that makes the network very, very sparse. However, when you need to model such a network, you need to deal with the computation on the scale of the number of nodes, not the number of edges. And that make the computation scale very quickly when you want to consider the entire population as your subject study. On the other hand, people say, why not you just sample the individual you're of interest and then just study the network that they are involved in. The problem is that even the network is sparse, it's still very widely connected. So a subgraph only using node sampled does not always carry the same dynamic topology of the entire network. So it's still desirable to study the entire network as a whole, but you need to deal with both the dimension of the problem and the sparsity of the data. So one way to deal with such a large scale of computation is through the stochastic variational inference. That being a Bayesian model, we apply the variational inference as an alternative to the Monte Carlo Markov chain computation, MCMC algorithms. The variational inference change a sampling problem of MCMC, which is more computational intensive, into a optimization problem that to approximate the posterior distribution, approximate the product through the optimization of a goal. So stochastic variational inference further improve the computation complexity of the problem by divide and conquer, by break up the bigger problem into small steps, and each step you only consider a random sample of data, and then it carried benefits. People found out that the stochastic variation inference actually optimize the target function much better, because if you have using all the data point, you may easily stuck in one local optimum, and using stochastic variation inference, sometimes you have better chance of reaching the global optimum thanks to the stochastic variation of the algorithm. So what it does is that they update the model parameter using random sample subgraphs, and then random sample for vector data is really simple. So you have, say, I want to create a Bayesian model using matrix data, not network, matrix data, to predict like your risk of getting COVID infection in the next 3 months or something. So I study not using the network, using everything I know potentially about your behaviors, and I create features. When I need to do stochastic variation inference, it means that I will sample a few individuals at a time to optimize that predictive modeling. So that is really easy. Sampling is a very well-defined, meaning that I just select individuals. For graph, sampling is an open problem. When you say a sampling graph, and you read papers and they say we create random sample for the graph, you first thing should say, what do they mean by that? It's not automatically that defined. So here for stochastic variational inference, when you need to create a sampling of a graph, you can sample nodes, you can sample edges, and most often people sample node pairs, and you can have pair of, because we need to update local parameter and global parameter for the graph. So we sample node pairs. There you have a few options. You can sample pairs of nodes, which are edges. You can sample nodes and select linked pairs. So you sample node first, and then you sample their linked pairs to prioritize links. You can sample nodes and select all its pairs, that is links and non-links. And all of these are possible and not perfect. They're probability samples, meaning that you can, once you have probability, you know how they're chosen, you can adjust them in the calculation, but they still poses biases in the inference, and then often people need to discover the biases post the calculation, post inference, and correct for the sampling biases. And then in dense network, these strategies would work because you can have a large enough probability to identify meaningful edges. But when you deal with a large network with sparse edges, we're not talking about sparse as we don't know each other, we don't have social interaction. It's just by the nature of social network, the number of edges does not scale with the number of nodes. So that's the definition of sparse network. That will lead to noise estimate, because if your sample is a small fraction of the entire network, the chance of you getting edges is very small due to the nature of the network. So I had done a lot of research in aggregated relational data for some other applications which I will talk about later. At one point we said whether such a method can create a opportunity for such network sampling need in the stochastic variational inference. So here we consider two papers, we all read papers, and then here I hide every information about the paper, the topic, the content, but I only show you which paper they cite, right? So consider two papers cited by a machine learning paper on networks, and paper one cite a total of 30 papers. Paper two cite a total of 32 papers. They're very comparable in terms of how many papers they cite, the total connectivity. And the first one cite JASA, which is Journal of American Statistical Association, 3 times, Social Network, the paper called a journal called Social Network 5 times, and a Journal of Mathematical Sociology 3 times. And the second paper cited Science 6 times, Social Network twice, and American Journal of Sociology 3 times. So the two papers definitely share similar citations, but they're also different shift in the discipline they cite. So you can get a sense of what the first paper might be about, because we know JASA is a methodology journal. They publish statistical methods, and social network studies network methods, and the mathematical sociology seem to be touched upon the mathematical network. So the first paper, you can get a sense that it must be a methodology paper that study network, and then also I have application in social science. The second one cited Science 6 times, and then doesn't seem to have any citation about statistical journal. So it could be about network, because it does cite social network and sociology, but it's more science than method. So you can see that this is what I called aggregated relational data, that we still talk about links, we still talk about citation links, but I do not look at individual links and aggregate them into counts towards certain subgroups of the population, right? So it's like how many, I will talk about that, how many people do you know analogy. So here is to reveal that the paper one is called Estimation and Prediction for Stochastic Block Structures, is published in JASA itself. And the second paper is Identify Influential as Susceptible Members of the Social Network. And you can see that the first paper is a methodology, the second paper is more of a science. So you can see that there is, according to our definition, is densely connected and also similar patterns. So these are the kind of thing we believe we want to detect using models, and aggregate relational data could carry such information. So the aggregate relational data was proposed initially to study something called hard to reach subpopulations. It was first proposed to use survey questions of how many X do you know when X represents a subpopulation of interest, such as, so the original survey has questions such as first names, how many people with first name Michael do you know, have a group membership, how many police officers do you know, and has experience, how many people who gave birth to a baby in the past 12 months do you know. So these, and you can see that people, women who recently gave birth to babies potentially know more other women who recently gave birth, simply because they share both social experiences and the physical encounter, higher chance of physical encounters if they go to hospital and go to checkups and stuff like that. So these are the kind of information we can leverage by understanding social structure. And then after you get the social structure identified, you can use them to infer hard to reach population when you have less knowledge about. So in the original publication, they were trying to use these known structures to study high risk populations, such as homeless population or population who are HIV positive or who are illegal immigrants. These people, you don't have a sampling frame to study them, but leveraging social structure, you can learn a lot about them without reach to them out to them directly. So it used to be, I used to need to tell people a lot about the literature of the ARD, but fortunately, in 2021, there is this very nice review article came out of JASA called 30 Years of the Network Scale-Up Method, another way that this literature is called, that touch upon many models has been used to study that from the social science perspective. So in my research, we have discussed that we can imagine that this is node, and we has a social position, a location in the social network, and its connection to other groups of that is being guided by a unobserved social distance, and our role is to estimate that social distance, and we estimate that social distance into a matrix. And here, this bar plot is similar to the B matrix that I first mentioned. That is an interaction between different social groups. Here, that the social group is predefined rather than discovered, but share the similar flavor. And here we have these female egos and male egos, and then here we have female alter, male alter. So in a nutshell, because it's a little small on the screen, that we're saying that basically men knows more men, women knows more women, and then it's called homophily, that people in social sciences and people have similar demographic background tend to have stronger social ties, and also is clustered by age, that you have this is the younger people, so the link is shifted downwards, is younger, and this is older individuals, older respondent, and their social type shift upwards to indicate homophily. So we also discovered in my research that in order to detect meaningful social structure, the design of the questions are also very important. What do you ask? You cannot ask everyone a question that's very biased. For example, how many you cannot, for example, you cannot only use male first names and how many Michael, John, Robert, because that will cause a shift in the responses that will be hard to correct in post inference. So here we use simulation to illustrate that if you have a ground truth that is a matrix look like something in the middle, and then if you have hidden population that is very, very clustered in the social space, that you'll have a hard time recover them. So you'll try to recover something here in this shape. And if you use population that are very, very clustered, then you will not be able to recover the structure. So which give us idea that one, aggregate relational data is very useful and informative, but they're only informative when you are aggregating the relations in a structured and meaningful way. So how do we do that for the open problem? So here that we are proposing, we want to model the entire full network as mixed members of stochastic block model. We're not changing our goal. We're still doing that. We're still doing, I want to do stochastic variational inference. However, when we create random graphs, random subgraph for the mini batch or whatever you call them, we want to use the ARD mini batch, which means that we sample the nodes, and then for each node, instead of choosing which links, which edges we're going to use in the neighborhood of this node, we will calculate its aggregated connection with meaningful subpopulation out there. So that allow us to focus on both global connectivity and the subsample, which was inspired by citation counts. That if you want to know whether a paper worth reading, sometimes you read the abstract, but if the abstract is not available, you look at the reference list. That's why people share the reference list publicly, because that allows you to see whether that's some paper that touch upon relevant literature. So which require us to model the aggregate linked ARD to infer the block model for the mixed membership stochastic block model. And then here, this is the difference that the typical mixed membership stochastic block model use the for each of this, you model each edges through this. And here, if we use aggregate relational model, we do not use the Yij directly. Rather, we use the count for subpopulations. And with very mild assumptions, we are approximating the distribution of Yik using a Poisson distribution, which make a great easy connection with the rest of the inferential process. And then our model inference is through variational inference, and then we propose the typical fully factorized variational distribution for the posterior distribution. We try to approximate, and then here the only and then we all know that in the variational inference that the goal is to optimize over the space of the variational parameter to identify, to minimize the the divergence between the variational distribution and the true posterior by minimizing the so-called lower bound on the log marginal likelihood. And then for this particular inference that the computation does not have a closed form, or the gradient can sometimes be hard to derive for the optimization, we adopt a statistical trick. Every time when something is hard to optimize, you can introduce auxiliary parameter or a further hidden parameter that make the computation easier given the auxiliary parameters. Then you try to minimize, optimize it further to minimize the difference between a lower bound to push it closer to the goal you try to optimize. It's similar to the idea of the EM algorithm in statistics, and then by expanding the model space, make the optimization easier, and then calculate the expectation to bring the likelihood even higher. So So another practical consideration is for large networks is often very hard, large models is often very hard to initiate a computation. When I work with my doctoral student and they read papers and of a large inferential algorithm of latent variable models, I often ask them, how do they initiate the inference? Because if you start very far away from the optimum, there's no guarantee that you're going to convert over, because nowadays we deal with non-convex optimization all the time. So it's very critical for us to understand how to initiate. Good thing is that with ARD, that we also have a natural way of initiate the analysis, is that we can compute the ARD as a preparation step. We need to do it anyway, and that give us a bipartite network, which we can use some rudimentary clustering algorithm to initiate the group assignment, and that bring us to a very good place automatically. And then we also, under this algorithm, converge very quickly. Usually, we don't see any further improvement after 3 passes, and each pass involve a fully iteration through all the mini batches. So if using the deep learning literature, it's like 3 epochs. You don't have to do like doing further. Does not improve the fit further. So that after every epoch, you will update the global parameter in the B matrix, and then the local parameter concerns the individual nodes location, the probability vectors that we talk about for the mixed membership. And so here we first check whether our model works through a small scale simulation where we can know the ground truth and then also iterate many times. We consider a network of 10,000 nodes, and then we generate a subpopulation centers and then generate node membership from these centers. And then we first draw for each of the node, we draw for each of the center of the subpopulation, we draw the center from the Dirichlet distribution, and then for each node in the network, then we also assume that it is a perturbed version of the center. And then we were able to show, the font is a little bit small, so you just have to believe what I'm telling you, that the method worked reasonably well, that this on the very right hand side is our method, and it reached similar performance in terms of community recovery than when you use a full network. I said that considering we only use 500 nodes, we sample 500 nodes and try to infer the community structure at a time, and this is a very good performance. And then it's definitely better than when you only use a subgraph of 500 node, much better than that. And this is the parameter recovery of the B matrix, which is another important matrix we try to recover, is how the community is organized. Like how do they connect within, how do they connect between? And then one thing interesting is that we see a reasonable recovery. So this is the full network and stochastic variation inference. They definitely have higher variability, and then our ARD has lower variability, and we see a small bias here, and we believe this small bias was due to the Poisson assumption that we have for the data, which may not be true for the network we're simulating, which is denser than a typical sparse social network. And when you have high probability for the binomial distribution using Poisson assumption, will lead to a small bias, and we believe that was the case here. So for real application, we're thinking about we use this KDD 2008 data set, which have 25 million edges among 3 million nodes, and then we use the citation network because citation network have a natural aggregated relational structure that you naturally can count the journals they're citing. The journals are natural subpopulations, and we just use all the journals as our potential subpopulation, but we don't use all of them at one time. We also iterate through them. And we remove journal papers that are isolated, do not have any outlinks, and then and which result into about 2 million papers and then 4,000 over 4,000 journals, and this data set is described in this 2008 paper, and this can be downloaded, publicly available. And we set a number of community 20 at each time for the mini batch, so we will iterate through our mini batches of 1,000 mini batches, 20 community at a time, and use all the journal as subpopulations. And then we use each of these have about approximately 2,000 papers, and then we stop when the elbow converges. So community detection is a unsupervised learning problem of clustering, and then whenever you do unsupervised learning, the hardest thing is how do you tell people it worked. So we spend a lot of time thinking about what kind of insight we can derive out of the outcome, rather than just saying we can predict a link, which is useful, but it does not tell us much about citation network as a whole. So we developed this visualization of the results. We call them a journal terrain profile. So this, for each of the journal, we consider the 20 cluster. We modified the 20 cluster is a static. We random sample papers that have membership in that group, weighted by the probability membership vector, and then we do a very simple word cloud to show what this is about. For example, this is about informatics right here, and here the keywords is communication, and then you also have science, machine learning, processing, so on and so forth. And then we did a very simple hierarchical clustering of this group so that they are arranged not randomly around the disk, but rather is being arranged by their proximity to each other. So naturally, that the topic on this end represent a lot of machine learning and analytic domains, where these sometimes is known as the hard half hemisphere of computer science, consider systems, security, the software, distributed computing, so on and so forth. So this, and then the membership, the location, the dots inside the disk is the combination of the location of the topics. So for example, each paper have a probability vector of 20, and you have 20 groups. So you, by the disk, all the 20 group is already around the circle. So the location of a paper can be calculated using the center of the circle and then multiplied by the probability circle. And then for each of the journal, we will random sample 1,000 of them. So plot them on the inside the disk. And we also have a contour plot. So these are, I think it's easy to see here. You have the lines here that represent the density distribution. And then you also, the color represents the topic. So you can see that a large concentration here with a non-trivial representation here. And then we also link to papers cited by the journal through the arc. So you can see that the journal's paper concentrate here, but also cites some of the systems paper, but mostly within its community. Remember, densely connected and also patterns. And this journal is the Journal of Machine Learning Research. So what we see is that it covers a broad range of topics, but not any topic in computer science. Half of the topics, not all the topics, but also is a very, very highly interconnected community. That the fact that you have 1,000 papers and they connect to each other in this way to cover the entire half of the disk is telling us that the papers are very highly connected. And then another journal is bioinformatics, which tell us a totally different story, that the contour plot is here. So when we first saw this plot, I was telling my student, you must have made a mistake. How can you have such a small contour plot? But that's the contour plot. For the 1,000, for the journal, for the paper associated with bioinformatics, they all have a very clearly defined identity. So they are here, and our method discovered that. Then this is here. And then, but it does, because bioinformatics is focused on computational biology and biomedical informatic applications, but they're not married to one tool, right? So they actually leverage a lot of tools, and the tools they use the most are artificial intelligence here. And then they also talk about, here is a mathematics processing. They sometimes talk about human education, interaction technologies. You also have other, here is a communication. So they do cover, some paper do cover those topics, but there is very highly concentrated, very locally concentrated, and have a strong tie with machine learning, because that's one of the primary tools used in bioinformatics. So we we designed this. It took us a few months to design this whole visualization to be very happy by the final product. It does. We have a shiny app that we made that show the journals. You can search up journals, and then out of curiosity, we applied the same visualization to the community detection done by this 2013 paper, which is a stochastic variational inference by estimating the mixed membership stochastic block model directly. And we found out you tell similar stories. The community are not as clean as what we have, and also the contour plot, the connection are also not as clean. So we discovered a more pronounced pattern of communities than using mini batches of sparse subnetworks. And we believe the noisy pattern we see here is because of the noisy subgraphs for the thing. And also there may be something true about the noisiness, the messiness you're seeing here, because citation is not just about community, it's not just about intellectual connection. Citation is a social behavior. It does not happen automatically. I know Eric, I look up his papers and cite his papers. If I don't know Hun, I may not know his research well. So I mean, even though he may work in similar area, I may not cite him as much. So it's a social behavior. By using journals, we actually suppresses some of the noises by aggregating. Aggregation is a noise reduction behavior. So we got clean community detection for two reasons. One is our computation is more stable because we're using more information in the data. Second, we also use aggregation, which project our model inference to a subspace of the community that is more stable. And then that shows another way to check citation network inference is always through the predictive ranking of links. And here we can see that if you use SVI network, you are able to predict the link more accurately because they're using the full network information, and the ARD has a comparable performance, but not as strong. The reason for that is we were able to discover the intellectual research community very clearly, but citation is a social behavior. We may be able to predict the journal very clearly, but we may not be able to predict the individual links of the of that. But we were very happy to see that by proposing a much more computationally efficient algorithm, we attained similar predictive performance. So to conclude, I think it's almost that we applied the aggregate relational data to scale up the model inference for mixed membership stochastic block model, and we leverage model information that primarily to reduce the model cost, but we end up finding that it has model inference benefits as a byproduct. The way we construct our data is highly parallel and can be accelerated with technology. And we believe it also lead to meaningful data reduction and protection if privacy is a concern, rather than saying, I don't have to tell you the title of the paper, but from the aggregate relational data, you can actually see the enough information for you to gauge the topic of that. So a lot of research are being done saying, what if we use keywords? What if we use such connections rather than share the for example, if one application we're doing is email networks, so rather than telling you, I can share my entire email log, which I will reluctantly refuse to do so because it contains a lot of private information. But what if I tell you I emailed 4 PhD students in statistics, 1 postdoc in computer science, 1 professor of climate science professor, and 1 dean that in the graduate school, and then guess what I do in the university. And you can see, oh, she's probably a professor of statistics who collaborates with climate science, who may also have some leadership role to play because she need to talk to the dean, or she may have. So this kind of information is a trade-off between data privacy and what we want to do, how much information we actually need for community detection. Community detection does not need the full detailed data. Community detection can be done through such aggregated data. So with that, thank you. I'm happy to answer questions.